Hi there. We're going to revisit an old topic called implicit functions and finding implicit derivatives. All right, the AP actually includes this as an extra topic after we finished all these topics of increasing and decreasing functions and concavity and all that sort of stuff, because we're going to go back and look and see where we might find vertical tangents, horizontal tangents, and then also tie it into where implicit functions concave up and concave down. So here we go. It's going to be a relatively quick video. We got three examples. You already know how to do implicit derivatives. I'll kind of give you a reminder as we go along, but we're going to tie this into our tangent lines and to our concavity. Just an introduction, we say that a function has a vertical tangent if the slope is infinite at a point, that is the slope's denominator is equal to 0, but the slope's numerator is equal to 0. That is if we have some sort of a fraction. And I give you an example right here of this circle, which we could define implicitly as x squared plus y squared is equal to 25. See that in just a second. But we get a vertical tangent, this little black dotted line right here, whenever the slope is infinite at a point, and a horizontal tangent if the slope is 0. So those are the blue dotted lines right here. And the slope's numerator is 0 and the slope's denominator is not 0. So again, if we were to find the slope of any circle centered at the origin, we get this derivative of dy dx is equal to negative x over y, all right? And we can show this down the road. In fact, we'll show it on the next slide. But I wanted to just show you that we get an infinite slope at any points when y is equal to 0. That's when your denominator is equal to 0, as long as x is not 0. So y is equal to 0 at this point, negative 5, 0, and at 5, 0. And then we get a slope of 0, a horizontal tangent, any points where x is equal to 0. That's when your numerator is equal to 0. And then as long as your denominator is not 0. If you get 0 over 0, you got problems, or you got different sort of things other than your horizontal or vertical tangents. But we notice right here, when x is equal to 0, we intersect at the point 0, 5, and at 0, negative 5. And we have horizontal tangents at those two spots. So let's do a quick little reminder. How would we find a second derivative of some sort of an implicit function? Well, we just take the derivative twice. So I say, suppose x squared plus y squared is equal to 25, the example we just saw, and we want to find the second derivative and evaluate it at 3, 4. All right, so if you remember, to find the first derivative, we take the derivative with respect to x. Derivative of 2x, or of x squared with respect to x is 2x. Derivative of y squared with respect to x is 2y dy dx. And of course, the derivative of 25 with respect to x is just 0. When you manipulate this, you get dy dx is equal to negative x over y. Well, to find the second derivative, we just need to do the quotient rule. Low d high minus high d low over low low. So we could say low is y, d high is negative 1. We're going to associate this negative with the x here. So we get negative y minus high d low. So we get a minus x times derivative of y with respect to x, which is dy dx, all over low squared, which is just y squared. So we get the second derivative is negative y plus x dy dx over y squared. Now we know what dy dx is. We can substitute that in because we know dy dx is negative x over y. So we plug that in. We also know we have the point x equals 3, y equals 4, so we can plug that in as well. And when we plug that in for the slope, we get negative 3/4 as the slope. And this simplifies to negative 25 over 64. Now, what does that mean for our implicit curve? Well, anytime the second derivative is negative, that means the curve is concave down at that point. And we can see right here, that makes sense. This little portion of the curve is concave down because it bends down, basically, at that point. All right, we also can tell that the slope is negative 3/4, so we have a negative slope here. So this is a negatively sloped concave down portion of the graph at that point 3, 4. All right, so here's another example. Suppose we have a curve x squared plus 27y squared equals 9xy plus 4. We can show that dy dx is equal to 2x minus 9y over 9x minus 54y. I'm not going to show that in this particular example because this is an easier implicit derivative to find, but generally on an implicit question, you're asked to show that dy dx is equal to something. So we're going to assume that we know how to do that here. Part A, find the coordinate locations of all horizontal tangents to the curve. Well, what do we need to do? Horizontal tangent will mean that the numerator is equal to 0 and the denominator is not 0. So here we want to make sure that dy dx overall is equal to 0, so that's why we're setting our numerator equal to 0, and we get 2x minus 9y is equal to 0, and so y is equal to 2x over 9. Now what does that mean? What that's telling us is that we've got the curve here in red, that's the x squared plus 27y squared equals 9xy plus 4. It's some sort of a shifted ellipse here. And this equation that we just came up with here, y equals 2x over 9, is telling us that we're going to get a horizontal tangent anytime the line y equals 2x over 9 intersects the graph that's in red. All right, and so what's going to happen is anytime we get any of those intersection points, as you can see right here, we can draw a horizontal tangent. And at this point where they intersect, we're going to get our two horizontal tangents. So to solve this, just like we solve any sort of systems of equations, we're going to take our y is equal to 2x over 9 and plug that into our original curve. All right, so I plugged in 2x over 9 in any time I saw y in my original curve. So when I do that, I get x squared plus 27 times 2x over 9 squared equals 9 times 2x over 9 plus 4. So remember, the whole point of this is we're going to find the x coordinates where these two graphs intersect each other. So some algebra happens. I do some simplifying. I get down to a statement where x squared over 3 is equal to 4. All right, and then when I solve, I get x is equal to plus or minus 2 root 3. That's telling me that these x coordinates where these two graphs intersect is at 2 root 3 and at negative 2 root 3. And then to find our y coordinate, we would just plug in 2 root 3 and negative 2 root 3, and we get into our equation y equals 2x over 9, and we get the coordinates 2 square root of 3, comma 4 square root of 3 over 9, and negative 2 square root of 3, comma negative 4 square root of 3 over 9. All right, so remember, we're just finding intersection points wherever our numerator was equal to 0 and finding by substitution where that point occurs on the curve. All right, final example here. Consider the curve xy cubed minus x squared y is equal to 2. First, we want to show that dy dx is equal to 2xy minus y cubed over 3xy squared minus x squared. So how do we do that? Well, we got this little thing called the product rule. So the first portion that we've got here is x times y cubed. When I take the derivative with respect to x, using the product rule, I get a y cubed times 1 plus a 3xy squared dy dx. That's the derivative of this first portion right here. Derivative of the second portion will be x squared times the derivative of y with respect to x, which was x squared dy dx, making sure to keep the negative there, minus a 2xy, and that's equal to 0. So again, I want to group all of my dy dx terms together. What that means is I'm going to add 2xy to both sides and subtract y cubed, and then I'll divide by 3xy squared minus x squared after factoring out a dy dx. And so I get the derivative that they want. All right, find the coordinate of each point on the curve where the tangent line is vertical. So remember, we need to find where the denominator is 0 and the numerator is not 0. So in this case, that means setting 3xy squared minus x squared equal to 0. Notice that I can factor out an x on my left side of the equation. So this is equivalent to saying that x times 3y squared minus x is equal to 0. So we start with the root x is equal to 0. Now notice, just like before, the whole idea is we want to see where the line, vertical line x is equal to 0 intersects the curve. So I put the curve right here thanks to a graphing utility that I have available. And we notice that x equals 0 never intersects this curve. And the reason for that is if I were to go through and plug in 0 into my curve, I get this nonsense statement of 0 is equal to 2. That's telling me right away that there's no situation where that occurs. And so we have no coordinates where x is equal to 0 on our curve, and so that particular solution set doesn't happen. We also can test where 3y squared minus x is equal to 0. So that basically gives us that 3y squared is equal to x. If you remember a little bit from your pre-calculus days, this is a conic section. All right, 3y squared is equal to x. And that's my curve here in blue. And basically, just like before, our idea is we want to find where that blue curve intersects the red curve, because as you can see, where they intersect, we're going to have a vertical tangent. So plugging into the curve, I'm going to substitute in x is equal to 3y squared. So I get 3y squared times y cubed minus 3y squared, all squared, times y is equal to 2. So all I did was I took x equals 3y squared and plugged into the curve. When I simplify, I get 3y to the 5th minus 9y to the 5th is equal to 2. All right, and I eventually get down to y to the fifth is equal to negative 1/3. So this works because we're going to actually be able to take a fifth root of a negative number. It's an odd root of a negative number. And we get this weird number, y is equal to the fifth root of negative 1/3. Don't panic, it's okay. All right. You'll probably see something like this on a calculator inactive section. All right, so you just leave your answer just like that. And since x is equal to 3y squared, I can plug in my y coordinate, and I got 3 times the fifth root of 1/9. So notice I squared the negative 1/3 inside my radical to get my coordinate. So therefore my coordinate is 3 times the fifth root of 1/9, comma 5, or the fifth root, excuse me, of negative 1/3, which is what this point right here is. So in general, we can find both first and second derivatives for our implicit functions and connect that to concavity. A vertical tangent occurs if the slope is infinite at a point. If you have some sort of a slope that's got a fraction, a denominator, and a numerator, that's where denominator is equal to 0, but the slope's numerator is not 0. And a horizontal tangent if the slope is 0. For a fraction, that means the numerator is 0 and the slope's denominator is not 0. Thank you very much. We'll see you in class.